what we're going to see with sample problem 19.8 is it's going to look very similar to what we saw for 19.7, which is looking at the solubility of calcium hydroxide as we put, for example, a chunk of this in solution. But what's going to be different is we're going to put this in a chunk of solution that already has a common ion in there. So let's actually read through this problem here. So it says in sample problem 19.7, we calculated the solubility of calcium hydroxide in water. So we'd like to know what's its solubility if we already have 0.1 molar calcium nitrate there. Again, we have the same KSP for this, so let's set this problem up and then see what's different. All right, start with an equation. Calcium hydroxide as a solid will be allowed to dissociate into calcium ions and twice as many hydroxide ions. KSP is equal to the calcium concentration times the hydroxide concentration squared, and that's 6.5 times 10 to the minus 6th. Haven't written anything different yet from what we saw on our previous calculations. ICE table, solids don't appear. 0.1 molar calcium ions. Okay, we see where things now are different from what we had on this previous problem. When we just had a pure water solution, we were assuming that there were no other sources of calcium ions. For this problem, we know that we have 0.1 molar calcium ions, and let's just make sure everybody sees where that comes from. We have 0.10 moles of calcium nitrate per liter. Calcium nitrate, all nitrate salts are soluble, so we're going to get 1 mole of calcium ions and 2 moles of nitrate ions when this completely dissociates. And we have to remember all nitrate salts are soluble, so that's going to completely dissociate. This is important here to kind of think about conceptually from a mathematics standpoint. Won't matter for this problem, but for every 1 mole of calcium nitrate we have, we make 1 mole of calcium, which basically means we're going to have 0.1 molar calcium ions that are already in solution. All right, so that's how things are different. We're going to assume that there's no hydroxide that's already in solution. The rest of the table is going to look the same as we had before in terms of our change column. 0.1 plus x, and now 2x. So just to draw a little picture down here and compare to what we had in the previous, all right, so if we've got a little tube here, we've got some solid calcium hydroxide that we wanted to put there. What's different here is we already have a solution that's got calcium ions and nitrate ions that are there already. Because we have this calcium already here, this is again what we call a common ion, that's going to limit the amount of calcium that can actually come from this breaking apart. We've already kind of filled up our reservoir a little bit with some of the calcium, so less of this is going to be able to break apart. If you actually want to think about it from Le Chatelier's principle, right, if we think about this as an equilibrium and we push in a product, that's going to shift our equilibrium to the left, which means we're going to have less of the calcium hydroxide that's allowed to dissociate. So our KSP here, if we actually solve for what our x is equal to 0.1 plus x times 2x squared. It'd be really nice if I could make an assumption, so let me do a little pre-check here. Pre-check means I'm going to take my concentration that I have and I'm going to put it over my K value, and that equals 15,385. So I'm definitely okay doing my assumption. And so we can simplify this, and our KSP, which is equal to 6.5 times 10 to the minus 6th, is going to be equal to 0.1 times 4x squared. Right? I actually should have had, I wrote this incorrectly here, 2x, the quantity, squared, which ends up being 4x squared. Go ahead and solve for x, and you're going to equal 4 times 10 to the minus 3rd molar. So that's the solubility. Remember, anytime they're asking for a question about what's the solubility, they're asking for what x is. And what we can see is that x is significantly different than what we got here. 1.2 times 10 to the minus 2nd, 4 times 10 to the minus 3rd. So it's about 10-fold less soluble. And again, that's because if we have this calcium ion already in solution, when we talk about how much of this gets to break apart and can contribute to the calcium and hydroxide ions that are in solution, not as much. So again, to point out here, for this problem, the calcium ion concentration is going to be 0.1 plus x. So let's go ahead and figure out 0.1 plus our x, which was 4 times 10 to the minus third, 0.104 molar, and our hydroxide concentration was equal to 4 times 10 to the minus third molar. Do you remember in sample problem 19.7, we took the concentration of calcium, which was 1/2 the concentration of hydroxide, and when we put those back into the KSP, we get 6.5 times 10 to the minus sixth. Putting these values for the concentration of calcium and the concentration of hydroxide, putting those values back into this KSP expression will still give us 6.5 times 10 to the minus sixth. And that's an important kind of thing to point out, because I think sometimes students think that when we have concentrations of calcium and hydroxide, in this example, in solution, they're always going to be in a 2-to-1 ratio. And that will be the case if you start with a pure chunk of something. But in this common ion problem, because we already started with some calcium in solution, we're not going to have as much of our salt be allowed to dissociate. And so we already have just some calcium there, so we just contribute a little bit to it. And then because we only contributed a little bit to it, okay, the X is still going to be twice for the hydroxide, but because only a little bit of it was allowed to contribute to the calcium, only a little bit will contribute to hydroxide. But mathematically, these two values put into the KSP will still equal 6.5 times 10 to the minus sixth.